Welcome. This brief presentation will show some science highlights from salinity and temperature observations in the deep Atlantic Ocean. My name is Matthias Langhorst. I work at the Scripps Institution of Oceanography, and this presentation is for the Ocean Sites meeting being held in September 2020. Our project is called MOVE, Meridional Overturning Variability Experiment. We make observations of the southward flow of North Atlantic deep water, NADW, across a section in the tropical Atlantic at 60 north, as shown on the map. NADW occupies depths below 1,200 meters, and its flow balances northward flow near the surface, such as the Gulf Stream, as part of the Atlantic meridional overturning circulation. The motivation behind our observations is that the overturning is an important component of the Earth's climate system. MOVE operates a mooring array with 3 sites. Directly at the western slope, the boundary current is observed with current meters on the M3 and M4 moorings. For the open ocean part of the section, from M3 all the way to M1, currents are derived from the thermal wind equation, that is geostrophy, using density observations made with the M1 and M3 moorings. Density is derived from temperature and salinity measurements, for which high accuracy is required. MOVE has made these observations since 2000. The figure on the bottom left shows the 20-year time series. The property shown is the ocean volume transport in units of Sverdrup across the MOVE section in the NADW layer. Negative numbers indicate southward flow. Large variability is seen, with an average near 18 Sverdrups southward, and excursions up to 10 Sverdrups around the mean. Thanks to the duration of the time series, we can also detect slower decadal scale variability, as highlighted by the orange line here. We believe that this interannual variability is one of the climate signals that we intended to observe in the first place. These figures are from a 2011 paper by Uvescent and co-authors. The rapid array at 26 north makes similar observations, and here we will take a closer look at density from the western sites of both the MOVE and rapid arrays, 16 and 26 north, shown on the map. The top right panel shows time series of density observations in the NADW at these 2 locations. Both curves show a consistent drop in density that occurred around 2010. A different way to show density is through the geopotential height anomaly, or dynamic height. The panels on the bottom right show this property, computed from 0 at depth upward, as depth time plots for the 2 locations. The transition from green to magenta colors corresponds to the density change seen earlier. The geopotential height expresses the thickness of a layer between 2 pressure levels. The units here are such that the layer thickness changes by about 4 centimeters between the dark green and the dark magenta colors. These are small changes, but they are the drivers behind the large-scale currents seen in the previous slide. For a closer look at where the density changes come from, the 2 bottom left panels show TS diagrams, temperature salinity diagrams, one from each site. Slant numbers inside the panels denote isopycnals in kilograms per cubic meters, and upright numbers are depths in meters. The different lines in the panels are 3-year averages from the mooring observations, with more recent years darker. We see that over the years, the TS relationship throughout the entire NADW range has shifted up and left, that is lighter, and this is observed consistently at both latitudes. The figures are from a publication by Eleanor Freika-Williams and co-authors in 2018, which contains more details and shows that the primary driver of these changes in density is a reduction in salinity. Bear in mind that the typical instrumental accuracy of salinity observations is around 0.005 grams per kilogram, and these observations push the limits of what is observable. In conclusion, we can observe small density gradients in the deep ocean with moorings, and have continuous time series of over a decade duration. These density gradients drive large-scale ocean circulation, such as the Atlantic meridional overturning. For reference, the most recent report that shows the data seen here is from 2020 by Denis Volkov and co-authors. To derive density with the required accuracy, we need salinity observations that push the instrumental limits. A 2006 paper by Torsten Kanzo and co-authors describes an in-the-field calibration method that is routinely done by both MOVE and RAPID, in addition to factory calibrations. This involves attaching the mooring instruments to a ship-based reference CGD system together with water samples. In the future, I hope that instrument development will continue to improve. Specifically, I am thinking about biofouling mitigation in the conductivity sensors, as well as better characterization of pressure sensor drift and calibrations and their temperature dependence. There is a working group on moored temperature salinity instrumentation by IAPSO, which will hopefully work these issues. For the science, I am hoping to see more time series that are several decades in duration, such that we can see decadal climate scale variability in direct observations. This requires funding mechanisms that can be sustained for longer times than typical one-off science projects, as well as consistent planning of staffing and material. All of these are challenging, but can be done. As for my own support in the MOVE project, I gratefully acknowledge funding by NOAA's Global Ocean Monitoring and Observing Program. Similar appreciation is due to the other data sources used in this study. And with that, I thank you for watching and hope you will participate in the Ocean Sites meeting. Thank you and goodbye.